You know that feeling when something works perfectly in testing, but the moment real people use it, it falls apart. It's like building a race car that crushes it on the track but breaks down in city traffic. That's exactly what happens with large language models. In the testing, they are incredible. They write essays, pass benchmarks, and impress your entire team. But the moment you put them in production, the cracks start to show. Your chatbot suddenly takes 4 seconds to respond. Your mobile app starts crashing, and your cloud bill, it skyrockets overnight. So what changed? The truth is, accuracy alone doesn't guarantee real-world performance. Out here, speed, memory, energy, and scale matters just as much. And without optimization, even the smartest model can feel unusable. Hi, I'm Gourav Agrwal, an applied scientist at Amazon AGI, and welcome to this NIIT Masterclass on LLM optimization for real-world deployment. In this masterclass, we are going to bridge that painful gap between research and reality. You will learn how to take a giant, brilliant model that dazzles in a notebook and turn it into something that's actually fast, affordable, and production-ready. Together, we will explore practical techniques that help you shrink massive models without losing their smarts, cut latency and cost without retraining everything from scratch. Here is a quick roadmap of what's ahead. We will start with model distillation, where small models learn to mimic big ones, then move into quantization, squeezing numbers down so models run lighter and faster. We will unlock speculative decoding, a clever trick to speed up generation without retraining. We'll explore efficient attention, which lets us stretch context windows without blowing up your memory. Look at real-world serving optimizations like caching and kernel fusion to make apps feel instant. And finally, we will dive deep into LoRa and PEFT, which are smart ways to adapt LLMs to new domains without minimal compute. Each of these techniques answer the same question in its own way: how do we make LLMs cheaper, faster, and more accessible without losing their magic? Before we dive into the how, let's step back and talk about why we should optimize the LLMs. Over the last 2 years, large language models have exploded in capability. GPT-4o can now handle text, vision, and even audio. Open source models like Mistral, Gamma, and Phi 3 are catching up fast. But here is the one thing, all of them are massive, and massive models are tough to use in the real world. It's one thing to run a demo in a lab or a Jupyter notebook, but what about deploying it on a smartphone, or serving billions of API requests, or powering a chatbot where users expect answers in under a second, not after 4 awkward seconds of waiting? Let me give you a real example. Earlier this year, a trend went viral, generating images in Studio Ghibli style. The demand was so high that OpenAI server was overloaded. Sam Altman, the CEO, even joked on Twitter, "Our GPUs are melting." That's what happens when models are powerful but not optimized for scale. Performance bottlenecks don't just frustrate users, they melt your infrastructure. So here is key mindset shift. Performance isn't about just accuracy anymore. It's about responsiveness. It's about memory footprint. It's about power uses, especially if you want to deploy on mobile or edge devices. And most of all, it's about cost. Because let's face it, a model that's 1% more accurate but 10x more expensive to serve, that's not a breakthrough, that's a blocker. The problem is only getting more urgent. Model sizes keep scaling, but hardware isn't keeping up. Consumer devices still choke on multi-gigabyte models. GPUs are scarce, and latency requirements are getting stricter, not looser. That's why optimization isn't some nice-to-have step at the end of the pipeline. It is the pipeline. It has to be baked into how we design, train, and deploy from day one. So that's what this masterclass is about. Not just making models smarter, but making them usable. And with that in mind, let's roll up our sleeves and start with a technique that's surprisingly intuitive and surprisingly effective: model distillation. Imagine you are a university professor You have spent years reading papers, building models, teaching machine learning to generation after generation of students. Now, you are mentoring a brilliant new engineer, someone quick, eager, but just starting. Would you just dump your entire library of textbook on their desk and say good luck? Of course not. You would do something better. You would condense what you know. You would share the key insights, the patterns that really matter, and the shortcuts that took you years to figure out. You would help them avoid dead ends and focus on what works. That's distillation. But instead of passing knowledge from teacher to student in a classroom, here it's between neural networks. In the world of LLMs, model distillation is the process of taking a large, powerful model, the teacher, and using it to train a smaller, faster model, the student. The goal? Pass on the teacher's knowledge but without all the overhead. And here is the twist. We don't just train the student on raw data, we actually train it to imitate the teacher's behavior. That means the student doesn't just learn the final answers, they learn how the teacher got there. During distillation, the student picks up on the soft probabilities the teacher assigns to different outputs, not just right or wrong, but how confident the teacher was, the hidden representation of the intermediate patterns that the teacher discovers along the way, and even the attention maps how the teacher decides which words in the input matters most. It's a lot like watching a chess grandmaster play. You are not just memorizing their final move, you are studying their thought process, their positioning, and subtle strategies that led to that move. And by capturing the process, the student model can act smaller, faster, and lighter while still carrying most of teacher's intelligence. This diagram makes it crystal clear. The same data flows into both the teacher and the student, but here is the catch. Only the student gets updated. The teacher already knows the material. The student learns by mimicking the teacher's responses and by studying its internal signals, the probabilities, the hidden layers, and the attention patterns. In other words, the student isn't just learning the answers, it's learning how the teacher thinks. Alright, so what does this look like in practice? Let's start with one of the most famous examples, DistilBERT. Now, DistilBERT is a compressed version of the original BERT-based model. It shrinks from 110 million parameters down to just 66 million, almost half the size, and yet it still retains about 97% of BERT's performance on the glue benchmark. How does it do that? By mimicking BERT's behavior at multiple levels, the output logics, the embeddings, and even the attention distributions. This diagram shows exactly how DistilBERT compresses the original BERT base architecture. On the left, you see BERT base. It takes in tokenized text, passes it through an embedding layer, and then stacks 12 transformer layers before producing its final output. It's powerful but very heavy. Now look to the right. DistilBERT keeps the same skeleton but trims the depth in half. Instead of 12 transformer layers, it only has 6 transformer layers. It also removes some extra components like token type embeddings and the pooler. The result, a model that is leaner, faster to run, and far lighter to deploy while still preserving almost all of BERT's intelligence. Next up, TinyBERT. TinyBERT takes things even further. It's just 7.5 times smaller and nearly 10 times faster than BERT base at inference time, and yet it still performs competitively across a range of NLP tasks. Its key trick is layer-wise distillation. Instead of only copying the teacher's final outputs, the student is trained to align with every layer of the teacher. That means during both pre-training and fine-tuning, TinyBERT is shadowing the teacher's thought process step by step. Think of it like mentoring your junior engineer, not just on the final code they ship, but also reviewing every draft, every sketch, every iteration along the way. This diagram captures how TinyBERT goes through two phases of distillation. Phase 1 is general distillation. A large text corpus is used to transfer broad general knowledge into a smaller general TinyBERT model. Think of this as giving the student a solid foundation across a wide range of topics. Phase 2 is task-specific distillation. Here, a task dataset, say for sentiment analysis or question answering, is expanded through data augmentation. That enriched dataset is then distilled into TinyBERT, refining it for specific task at hand. The result is a fine-tuned TinyBERT, a model that's not only compact and efficient, but also specialized for real-world use cases. And this two-step process is what makes TinyBERT especially powerful for constrained devices and latency-critical applications where every millisecond counts. And finally, let's talk about DistilGPT2. DistilGPT2 is the distilled version of OpenAI's GPT-2. It reduces the parameter count from 124 million down to about 82 million. That might sound like a small change compared to the BERT family, but the effect is big. It's lighter, faster, and still produces impressively high quality text. During training, it uses techniques like cosine embedding loss and output token alignment to mimic GPT-2's generation style. So where does it shine? Real-time writing assistants, customer-facing chatbots, and creative tasks like storytelling anywhere you can't afford multi-second latency spikes. Of course, like all compressed models, there are trade-offs. Sometimes the fluency dips or the creativity narrows. But that's the balance of distillation, speed versus fidelity. So when should you actually reach for distillation? The answer is simple. Whenever latency is critical, if your app has to run on a CPU instead of a GPU, if it needs to fit on a mobile device, or if your cloud inference bill is spiraling out of control, distillation can be a lifesaver. It gives you a way to scale LLM capabilities without scaling infrastructure costs. To recap, distillation is the process of teaching a smaller model to behave like a larger one. The student doesn't just memorize the answers, it learns from the teacher's outputs, embeddings, and even the attention maps that reveal how the teacher focuses on information. And we have seen it in action. DistilBERT cutting BERT's depth in half but keeping 97% of its performance. TinyBERT, layer-wise distillation 10x faster, perfect for constrained devices. DistilGPT2, light, quicker generation for real-time text tasks. Each one proves to the same point. With the right training, small models can punch far above their weight. But here is the thing. Distillation, as powerful as it is not magic. Like any optimization technique, it comes with its trade-offs. So the real question isn't just should I distill my model? It's when does distillation shine and when does it stumble? And that's exactly what we will break down next. Model size is the obvious win. Distilled models are lean, sometimes up to 10 times smaller. That means faster cold starts, lower memory uses, and yes, cheaper deployment. But that smaller size can mean a narrower understanding of edge cases, especially if the teacher had a wider context window or deeper capacity. On latency, you get a real performance boost, especially important if your app is interactive like a chatbot or voice assistant, but sometimes you lose subtle language behaviors. It's like asking a great student for a summary instead of a professor. You will still get the main points, but maybe not the edge case brilliance. Training-wise, distillation is relatively low effort if you don't start from scratch. But if you do need access to the teacher model, and often the original training data, which isn't always open source or portable. In terms of deployment, distilled models open up possibilities for edge and mobile use where you simply couldn't run the original model. But if you are already working on GPU-backed infrastructure, the need to distill might not feel urgent. And finally, quality. In most cases, you keep around 90 to 97% of the original performance, but in high stakes or nuanced domains, think medical diagnostic or legal writing, missing a few percentage points can really matter. So we have unpacked the what and why of distillation, this elegant teacher-student framework that lets us keep the brains but lose the bloat. Now it's time to make this real. Let's head into our first hands-on lab. We are going to distill GPT-2 using Hugging Face's DistilGPT2 pipeline and see for ourselves what the speed-quality trade-off really looks like in action. Ready? Let's build. In this hands-on lab, we will use Hugging Face DistilGPT2 pipeline to distill a GPT-2 model. You will see firsthand how a compact student model can retain much of the teacher's quality while drastically improving speed and efficiency. We will walk through how to invoke a pre-trained distillation setup, how to evaluate the BLEU score or perplexity for generation quality, and compare model size on the disk, inference speed, and output fluency and coherence. By the end of this lab, you will know how to evaluate trade-offs between size and performance, not just in theory, but in your own workflows. Let's dive in. So here we have a Jupyter notebook. I'm using a runtime GPU runtime, which you can change here. So I'm connected to a T4 GPU. You need any minimal GPU to support this distillation. Okay. First, we are installing all the dependencies which are required to run this module. So as you can see, we are importing auto model for causal LM, auto tokenizer from transformers. So first one is required to load any pre-trained model which is available in Hugging Face, and auto tokenizer is required to load the relevant tokenizer for the pre-trained model. And then we are also importing some basic utilities like uh, time, math, and torch libraries. Then we are importing some loss functions, KL divergence loss and cross entropy loss, which we are going to use for distillation. Then we are importing an optimizer called Adam Optimizer. As you can see, this will also be required because we are going to do a training as well. Then we are using this import dataset to load a dataset which is already available, so we don't need to procure or process any new data. So in this exercise, we are using GPT-2 as a teacher model, which is roughly 124 million parameters. And then we are using a DistilGPT2 as the student model. This is roughly 75 million parameters. So as you can see, first we load the tokenizer for both the models, and then we are loading both the models, and then we are shifting the model to device, CUDA device, using this .2 function, because we want to do the computation in CUDA or GPU. So that's why we are doing it. Now, first of all, we are comparing the model sizes. So as you can see, we have the output from this cell. Our teacher model is roughly 470 MB, which makes sense because we have around 120 million parameter, and each parameter is taking roughly FP32, which is 4 bytes. So that's why we have around 4 times the size. Similarly, our student is 310 MB, which is roughly one third less than the teacher model. So this is our basic models using which we are going to do distillation. Let's compare the inference speed from both the models. Since teacher is a larger model, you will expect its response to be slow, while the student would be faster. So let's see. We have defined a function here called measure time. This function basically takes a model, a tokenizer, and inputs, and we also provide the n tokens, which is the number of tokens we want to produce. Then we make a generate call, and we measure the amount of time it takes to generate those many tokens. This we will be doing for both teacher and student model. So I ran it for a prompt. Our prompt is artificial intelligence is transforming the world of. And now both the models need to complete this prompt independently. So let's see what we are getting in the output. So as you can see, teacher model is giving you this output. Artificial intelligence is transforming the world of business, and it's transforming the way we think about. So there are some, let's say 10 tokens produced by this teacher model. Similarly, if you look at the output of student, artificial intelligence is transforming the world of human race. It might make less sense, but our objective here is to measure the latency of each of the model, not the quality. As you can see, the teacher model is taking around 0.11 second, roughly 110 millisecond, while the response of student is taking only around 60 millisecond, which is around half of what teacher model is taking. So now we have seen that a smaller model will take less latency, and that was the goal of this cell. And now we will define how do we calculate the perplexity and how do we calculate the blue score. So in this cell, you can see first we are loading this publicly available data set called Wikitext. This is basically your featured articles on Wikipedia. So it's a clean data set. We are taking only 10% of validation split because we want to run this cell quickly. Then we are defining this function to calculate perplexity. Perplexity basically tells you, it's basically the exponential of likelihood of your outputs. It basically tells you how certain your model is in the output. So we will calculate perplexity one by one for both teacher model and student model. So let's run this cell. You don't need to define this function. This is available from some libraries as well. So you don't need to write this always. Now here you can see the perplexity of teacher is 20.86 and the perplexity of student is 33.22. So teacher model is having less perplexity. It means it is more certain in its predictions, while the student's perplexity is higher, which was expected because student is much smaller in the size. The learning and patterns it has less than what teacher model has learned. Now moving on to the blue score. Here we are calculating blue score again for both the models. Blue score is your bilingual evaluation understudy score. This is was first proposed to measure the quality of machine translation systems, where you are, let's say, converting your English sentence to French sentence and all those kind of things. Now here we have a couple of texts. So we are having three texts, and we will take the average of these to calculate the blue score. Now what you can see here is that first we are filling this list called references. So we just appended this static test amazing ways in all the prompts. So this is our reference, this is our ground truth, and then we are passing these inputs one by one to both student model, and we see that student model is generating something which we are appending to our predictions. Now we have both the predictions and references as a list of string, and now using this library which we have imported already, this blue library, we are computing the blue score. And as you can see, the blue score for student for these three sample text is coming out to be 43.36, which is very high, but given the size of the model, we can work with that for now. Now we will see how we can improve this distillation model by doing a sample training. So moving on to the distillation training part. Now first we need a training data set. So what we are doing, we are taking the train portion of our Wikitext 2 row v1 data set, which is again publicly available, and then we are filtering out all those samples where your text is either null, it's basically a string which is having a length equal to 0. So we will remove all of them so that we do not face any issue during the training. We need to define the optimizer. So we have Adam optimizer, and then important thing here is, you see, we are passing only student model dot parameters. It means we are training only the parameters of student model, not training the parameter of teacher model. These two are our loss functions. Then again, important thing, we are setting student model to train mode, and we are setting teacher model to eval mode. Now we are iterating our small training data set step by step. In each step we take a batch. We do a forward pass using the teacher model. As you can see, we do a forward pass using student model. We have the logits from both of them. Now once we have the logits from both models, we can calculate the Kale divergence loss as well as cross entropy loss. Our total loss is the weighted summation of both the losses. And now we do a loss dot backward, which will actively update the parameters of your student model. If I run this cell, you will see that we are training 10 steps for our student model. Our loss is coming down, but then it suddenly goes up at 9th step because this is a very small demo training. So training is not stable. We might have to change the learning rate and all those parameters, but you get the gist of the thing which I wanted to cover. And now let's review like what all did in this notebook, so that we can summarize our learnings from this notebook. So first is we looked at the size comparison between the teacher model and student model. While the teacher is 475 MB, student is only 310 megabytes, which is already around 65% of the size. Then if you look at the inference speed, our teacher produced the response in 110 milliseconds, while student produced the response in only 60 milliseconds. If you look at the perplexity, the teacher was having low perplexity while the student was having high perplexity. Now our takeaway is that DistilGPT2 is smaller and faster, and it can be further improved with the distillation training. Okay, so in this session we have seen how does the distillation work, how do we load teacher and student model, how do we compare the NLU performance using blue score and perplexity, and I also introduced you with a dummy training setup to make your student better. In the next step, we will learn about the process of quantization and how to run it in a demo notebook. So, we have seen how distillation works, passing knowledge down from a big teacher to a smaller student, like mentoring a junior dev instead of hiring a senior engineer. But what if you don't want to train the student at all? What if you want to keep the same model, same architecture, same logic, and just make it lighter, leaner, and faster by trimming the fat? That's where quantization comes in. Imagine you are moving houses. You've got a giant truck filled with beautiful functional furniture, but when you get to your new apartment, the hallway is narrow. You could try showing that couch, though as is, but chances are it won't fit. Or you could break it down, make it tighter, and reassemble it inside. Same function, smaller footprint. That's quantization, but instead of couches and tables, we are shrinking the numbers inside a neural network. Most large models, GPT, Llama, and Claude, are trained using float 32 precision. That's 32 bits for every single number in the model. Multiply that by billions of parameters, and suddenly your model is the size of a hard drive. But here is the real question. Do we really need 32 bits of precision just to generate a sentence? Turns out, not always. For many real-world applications, we can shrink those 32-bit numbers down to 8-bit integers or even 4 bits with only a few tiny dip in accuracy. And the effect? Models that once took hundreds of gigabytes now fit on a laptop or even a phone. Now, quantization comes in two main flavors, each suited to different needs. The first is Post-Training Quantisation or PTQ. Think of this as no prep compression. You take a fully trained model and apply quantization after the fact, and now it's smaller and faster. No retraining needed. PTQ is perfect for inference-only scenarios like serving models on CPUs or deploying in places where retraining isn't an option. Tools like Bitsandbytes, ONNX Runtime, and Hugging Face Optimum makes PTQ easy to apply in practice. But if you can retrain, there is a second option, Quantisation-Aware Training or QAT. Here the model is trained while simulating low precision math. In other words, it learns from day one how to live with fewer bits. The payoff? Better accuracy, especially for tasks where tiny details matter, like nuanced classification or structured generation. QAT is more complex and heavier upfront, but the quality gains often makes it worthwhile. Popular tools here include Intel Neural Compressor, PyTorch's QAT modules, and NNCF. So far, so good. But what exactly gets quantized? Is it the weights? Is it the activations, or both? That's what we will dig into next. Let's start with the weights, the model's learnable parameters. These are the billions of numbers that define what the model knows. Quantizing weights gives you the biggest savings in storage and memory, and the activations are outputs that gets generated at each layer as the model processes inputs. Quantizing activations helps cut down runtime memory uses, which is especially critical if you are deploying on low RAM environments like phones or edge servers. Now here is the important part. Quantization doesn't just mean turn everything into int8. You actually have a menu of formats, and each one balances size, speed, and complexity differently. Float 16 or FP16, half the precision of float 32, double the speed, widely used on NVIDIA GPUs. Float 16 or BF16, this is Intel's go-to training, keeps dynamic range while saving bits. Int8, the workhorse for deployment, most widely supported across GPUs and CPUs. Int4, ultra compressed, super fast, super small, but also much trickier to tune and prone to instability. Think of it like a photo quality settings. FP16 is like going from RAW to a high quality JPEG, smaller but still sharp. Int8 is more like a compressed web image, light, fast loading, and still good enough for most uses. And now Int4, that is like an aggressively compressed thumbnail, usable but not for everything. Of course, every optimization comes with its trade-offs. Quantization can slightly lower accuracy, especially for nuanced text generation or multilingual tasks, and not every piece of hardware supports every format equally. So you need to check what your deployment environment can actually handle. That's what tools like Bitsandbytes, Intel Neural Compressor, and NNCF shine. They don't just quantize blindly, they come with calibration presets and heuristics that make the process safer and more reliable. So where is quantization making a real difference today? Chatbots running on low-cost CPUs, language translation apps are running right on your smartphone, real-time summarization on edge servers with zero GPUs. These aren't research demos anymore. These are production systems serving billions of users every single day, powered by quantized models under the hood. The bottom line, quantization is one of the lowest hanging fruit in LLM optimization. It's often as simple as running a tool, and the benefits are massive. Faster inference, smaller memory footprint, and flexibility you would never get with full precision models. It's not about cutting corners, it's about carrying only what you need and leaving behind the bulky float baggage. So let's recap before we roll up our sleeves. Quantization shrinks models without retraining from scratch by reducing precision from float 32 down to int8 or even int4. You have seen the two main approaches, PTQ, Post-Training Quantisation, which is fast and plug and play, and QAT, Quantisation-Aware Training, for higher accuracy when quality matters. You also know what's getting quantized, weights for the size, activation for runtime memory, and the common formats in play are FP16, BF16, int8, int4. So far, so good. But theory is only half the story. The real magic is when you try it yourself. So ready for a hands-on? Let's dive in. In this lab, we will take a pre-trained language model GPT-2 and apply quantization. By the end of this lab, you will understand how to plug quantization into your Hugging Face workflows, when to use PTQ versus QAT, how to benchmark trade-offs for latency, memory, and performance. Ready to shrink your LLM and deploy with confidence? Let's dive into the code. So we are again connected with a T4 runtime GPU, and our first cell, we are basically importing all the dependencies which is required. So we have transformer 4.42, we have NumPy, PyArrow, and then we have these libraries, Bitsandbytes, ONNX and ONNX Runtime. These are relevant for the quantization process. ONNX and Torch is a different runtime. In ONNX, we do not have a concept of fully connected layer or attention. It's all about matrix multiplications and all. While in the case of Torch, we have abstractions like what is a linear layer, what is the attention block, and what is the LM head and all those things. And then we again import some utility based libraries like time, math, JSON, and all those. We are importing auto model for causal LM, auto tokenizer, and bits and bytes config from transformers. This will help us in loading the pre-trained models, loading the corresponding tokenizers, and any quantization config if available. So in this notebook, we will be working with GPT-2 model, which is the smallest model of GPT-2 family. It has roughly 120 million parameters. So we'll expect a size of roughly 480 MB, assuming a FP32 quantization. So let's fire this cell. Now in this cell, we have written a function to reduce the size in memory of any model. And here you can see that we are loading the model in FP32 precision. We are setting it to eval mode, and then we are transferring it to the device, whatever device is available, whether it is CPU or GPU. And as you can see in the output, when we are trying to load the model, first the tokenizer config is being downloaded, then model config is downloaded, then vocab.json is downloaded, and then we have generation config also, which is very relevant because this is the config where we set that what should be the sampling strategy or what should be the max number of new tokens and all those things. So as you can see, the size is reported as around 480 MB, which is 4 times the number of model parameters. Now let's move on to the evaluation cell. So here again we are using this publicly available Wikitext portion of data. We are using only 10% of data. Then we are setting the padding token as the EOS token from the tokenizer. We are defining a function where we calculate the perplexity for the text, and we do the chunking of the text first before calculating the perplexity. Right. So as you can see, we have set the evaluation data set. Now we are taking the text field of this data set, and we are joining all the text fields using these new line comments. So in a way, we want to calculate the perplexity for the all the text in all the samples in a single run. So that's why we are joining all of them in a single variable. Now we'll fire the cell, and this will give us the shape of the evolution vector, evolution input IDs, which is 1,512. Now we will move to the perplexity helper, where we have written a helper function to calculate the perplexity for any given test set. The input to this function are the model using which we want to generate the text, and then input IDs, which is basically the current prompts uh, in the tokenized form. And then you also pass the attention mask, because you need to tell the model whether it is a causal attention or it is a window attention. So there is this configuration. And then we have also defined a function to calculate perplexity in the ONNX mode. Now there you do not need the model, but you need to provide the session context in which the models and all those things will be loaded. So here we just define the function and we run the cell. Now we come to the function definitions to calculate the latency. So here also we have written two variations of the function. One calculates the latency if you are generating in torch, other one if you are generating in ONNX6. Here we have set, let's say, max number of new tokens, we have set the prompt, we have set the number of runs. All those things are useful in case you are facing any failure, so it will retry by itself. Now if you see, for each run we do the generation from the given model, and then we are recording how much time it is taking, and then we are taking the median of all those run times, so that we have a better average, because one single run could be extremely slow or extremely fast. So that's why it is useful to have multiple runs. Coming to the baseline metrics, so we have a base prompt, which is artificial intelligence is transforming the world of. And now if I try to calculate the perplexity for this given input prompt, I see that the perplexity is coming out around 23.76 for a full precision model on a CPU. And now I'm also calculating the latency for this model. I'm calculating latency using the torch variation of my function, and I see 2.47 seconds. Now let's see what if I quantize this model using bits and bytes, and then I will again calculate the accuracy and the latency. So we are doing post-training quantization here. We are not training any model with the quantization-aware technique. We have the GPT2 already downloaded on our system, and we will try to quantize it using 8-bit and 4-bit. So this is the code for this. Now you see, when we are loading the model using this library auto model for causal LM, we can provide a quantization config here. So we have provided that, okay, load in 8 bits equal to true, so it will ensure that the models are loaded in a 8-bit configuration. Let's fire up this cell. So it is doing two things. First, it is loading the model in 8-bit, then it is making the prediction for the given prompt, and it is also calculating the latency. Same thing then it repeats for the 4-bit variation also. As you can see, we provide that, okay, we want to do in 4-bit as well. Now if you look at the output, it runs very fast because we are running it only for the one prompt. But in real life, in your company, you may need to run it for a test set having thousands of examples, so it will take some time. Now if you can see here, when we have loaded the 8-bit model, the generation latency is now 1.42 seconds. Compare it what we were seeing earlier. We were seeing 2.47 seconds. So we can see that the model is definitely faster, but our perplexity has taken a hit. Earlier it was around 20, now it is around 24, which was expected, because as you are gaining more in the latency, you will be losing more in the accuracy. And you can see the model size has also reduced significantly. From 480 MB to it has come down to 157 MB using 8-bit quantization. If I talk about 4-bit quantization, the model size has reduced to 118 MB, but the perplexity has gone up, and our generation latency has gone further down. Our generation latency is coming out to be 0.824 seconds. If we compare it with the 8-bit, it was 1.42 seconds. So that's the magic of quantization. where you need to make certain trade-offs. You lose the accuracy, but you gain the speed up, and that's the trade-off you do for your quantization. So we have now seen how quantization lets you compress models without compressing value, trimming numerical precision for measure gains in speed and scale. But what if you didn't have to retrain or compress or still got a huge generation speed up? Up next, we will discuss speculative decoding, a technique that sounds almost too good to be true, but works like magic. So you have distilled your model, you have quantized it, it's cleaner, faster, and more efficient. But does your chatbot still feel sluggish? You type a message, wait, and then the response trickles out, one word at a time. What's going on? Well, here is the deal. The bottleneck isn't the model size, it's how the model generates text. Most LLMs use autoregressive decoding. This means the model generates one token at a time, and every token depends on the one before it. It's like writing a sentence blindfolded. You can't move forward until you know exactly what you just wrote. And that's where the lag comes from, even in optimized models. But what if we could break that chain? What if we could guess ahead and only go back if we were wrong? That's where speculative decoding comes in. Now you imagine pair programming, but with two models. You have got a draft model, which is fast like TinyGPT2, and a main model, which is accurate but slower like the full GPT2. Here is how it works. The draft model races ahead and quickly generates a few tokens based on the prompt. The main model follows behind, checking these tokens. If they make sense, it accepts them. If something is off, it rejects and degenerates them from the last correct token. It is the same idea that powers smart suggestions in tools like Gmail or Google Docs. You get a fast draft of what you might want to say, and then a smarter model comes in to clean it up. To you, it just feels snappy and efficient. Now, there are a few different flavors of speculative decoding. Vanilla speculative decoding is the one we just described. One draft, one verifier. It's simple and works surprisingly well. Now the other method is called EAGLE, efficient autoregressive generation via linear estimation. This takes things further. It uses beam search based decoding and smarter token acceptance strategies to speed things up even more. And then there is self-speculative decoding, which doesn't even need a separate draft model. The same model drafts and the same model verifies in alternating passes, kind of like thinking out loud and self-correcting as you go. So you might be wondering, this sounds clever, but does it actually help in real-world production? Absolutely, especially when token latency matters. Think chatbots, voice assistants, smart reply UIs, real-time code assistants, and anywhere a user is waiting on a generated sentence. And since the verification step is parallelizable, you can batch the token processing, further cutting down your total latency. And here is the best part. Speculative decoding works without retraining your base model. That's a huge win if you are serving a massive 13 billion model and doesn't want to spend hours fine-tuning. So, when would you use speculative decoding? If you are already using a large model and don't want to retrain, or you have got access to a smaller draft model which can be used as a draft, or your application is interactive and latency matters to the user. It is a neat trick. Fast guesses and smart checks gives you the best of both worlds. And when combined with techniques like caching, you can make even heavyweight models feel real time. Alright, let's try it for ourselves. In this lab, we will take a pre-trained GPT-2 large as target model, and we will use GPT-2 base variant as our draft model. By the end of this lab, you will understand what is a good draft and target pair. How do we do verification of draft candidates using the target model? So let's dive into the code. Now we have a Jupyter notebook where I am using a T4 runtime. It's a GPU based runtime because we are loading very large model. First, we will start with importing the required dependencies. So if transformers and torch library is not installed, we will install it using pip. Then we are importing auto tokenizer and auto model for causal LM, which we use to load pre-trained model weights and pre-trained tokenizers. So that is the first cell. Now in the second cell, First, we are declaring what is the target model and draft model. As you can see, GPT-2 large is our target model, which has 770 million parameters, and our draft model is GPT-2 base variant, which has around 117 million parameters. So you see the draft model is around 6x smaller than the target model. Ideally, we should have around 10x smaller draft model to have a very reasonable latency gains in the draft model. And then we are loading both the models using auto model for causal LM. Let's quickly look at the number of parameters in both the models. So as I was suggesting earlier, target model has 775 million parameters and draft model has around 124 million parameters. Now let's go about greedy decoding using the baseline model. So this is our greedy decoding baseline, where we are not using any kind of speculative decoding. This is just a simple generation. And then we are coming to vanilla speculative decoding. Now in this vanilla speculative decoding, I am first defining a function called speculative decode. Now the arguments are target model, draft model, the number of draft tokens, which is draft k. What does k represent is basically we generate 4 draft tokens before we go into the verification cycle from the target model. Once we are done with the verification, then we come back to the draft model, again generates 4 tokens. So that's how it works. Now inside this function, you can see first we are generating the draft outputs using the draft model. Then using the same input prompt, we are generating target probabilities from the target model. Now for each draft tokens that we generated, we are verifying each of the draft token one by one. What we do, we calculate we take the probability from the target output distribution, and we see if a random number between 0 and 1 is smaller or more than this probability. If it is less, then we accept this token, otherwise we reject it. In the case where we reject this token, we generate a new token using the target distribution of the target model. Otherwise, we keep repeating this loop until we exhaust all the draft tokens. At the end, we append all the generated draft tokens together and we return it back in our generation function. So this is our speculative decode function. Now we are defining the latency benchmark. Here we are declaring number of runs equal to 2 because it's always good to take average of multiple runs. So now our prompt here is artificial intelligence is transforming the world of, and using the same prompt, once we do the greedy decoding and once we do the speculative decoding. In the case of greedy decoding, you can see we are using only target model. In the case of speculative decoding, we are using a draft model as well as a target model, and we also need to mention the number of draft tokens. This is a hyperparameter. You can try number of draft tokens as 3, 4, 5, 6. Usually 3 to 5 is a good range. And if I run this cell, I can see that the greedy decoding is giving me a latency of 3.41 second, while the speculative decoding is giving me a latency of 1.2 second. So here you have your 2.85x speed up gain, which is very good. And you should also look at the output distribution, and you will see the quality is pretty much same. You can look at the output comparison as well to understand if the quality is very bad or very good or comparable. So from the first model, where I'm using GPT-2 large and doing greedy decoding, this is the output for the prompt. And for the speculative decoding, you can see the output is still meaningful, and it is not very far from the original model output because we are anyway doing the verification with it. So that is all about the vanilla speculative decoding. So we just saw how we can make the decoding faster using a neat technique called speculative decoding, where we don't have to trade off the accuracy for speedups. But now we are encoding context for both target and draft models, which means more computation and more memory requirement. Now let's jump to some efficient attention techniques which enable us to handle these growing compute and memory requirements in our system. Alright, so we have optimized the model, we have compressed the weights, sped up the decoding, but there is still one monster lurking in the background: memory, specifically attention memory. Let's say you are working with longer and longer inputs, 2000 tokens, 4000 tokens, maybe even 16,000 or more. you start to notice your memory uses ballooning. Latency spikes, your GPU chokes. The problem lies in how self-attention works. By default, attention computes pairwise interactions between all tokens. For n tokens, you need an n by n matrix, that is an order n square operation, both in terms of compute and memory. So as your input grows, your memory uses grows quadratically. That's why context window expansion is so expensive. But thankfully, we have got tricks to fight back some of the most exciting attention optimizations in recent years. Let's walk through a few of the big ones. The first one is FlashAttention. This is like the Formula One car of attention. FlashAttention fuses multiple CUDA kernels into a single memory efficient operation. It avoids writing intermediate results to memory, which slashes latency and memory uses drastically. Think of it like cooking a meal all in one pan instead of juggling 5 at once. Less cleanup, faster results. FlashAttention is already baked into models like Mistral and widely used in Hugging Face transformers. Traditional attention writes back to memory repeatedly. FlashAttention keeps everything in fast registers and outputs in one pass. Another efficient attention method is grouped query attention, GQA. Here, you group queries so that they share keys and values, reducing redundancy. It's a neat trick that allows you to scale the number of heads without exploding memory. Models like Longchat uses GQA to scale up context windows to 16K or even 32K tokens, even more, without melting your GPU. And the second variation is multi-query attention. This one takes GQA to the extreme. All heads are sharing a single set of keys and values. It is ultra efficient and particularly useful in decoder-only models like Llama or Gamma. You lose some richness in representation, but gain huge improvements in memory use and throughput. These aren't just research ideas, they are powering today's most scalable models. Mistral uses FlashAttention for speed, Longchat uses GQA to scale to long-form inputs, and Gamma combines MQA with quantization for efficient decoding. Together, these techniques unlock longer context windows, smoother real-time generation without doubling your hardware budget. But of course, fast models still need fast pipelines. So let's talk about serving tricks under the hood optimizations that make your model feel fast to end users. First up is KV caching. In decoder-only models, every new token usually means reprocessing your entire prompt unless you cache. KV caching stores previous key value pairs and reuses them, avoiding the redundant computation. It's like remembering what you said 5 minutes ago instead of repeating the whole sentence every time. The next trick is kernel fusion. This one is all about kernel overhead. Instead of running 10 small matrix operations with slow Python overhead, fuse them into one larger optimized kernel. You get lower latency, fewer memory transfers, and better throughput. And then there is tooling. If you are serious about real-time LLMs, check out the following. VLLM, a high throughput engine built for token streaming. Then there is Torch Dynamo, dynamically compiles PyTorch models for optimized graph execution. And then there is paginated KV cache, smarter caching that avoids unbounded memory growth as your context grows. All of this matters especially when you are building streaming apps like chatbots, code assistants, or transcription tools. If your model can't serve in less than 500 milliseconds, it won't feel responsive. These tools and techniques are how you hit those latency targets. Let's see KV caching and FlashAttention in action in a notebook. In this quick demo, we will compare model behavior with and without use cache equal to true. We will watch how caching impacts token latency. We will also test one of the open source models that uses FlashAttention and compare its speed to a baseline. Let's jump in time to make attention efficient. Now here, we are doing this exercise in a Jupyter notebook. We are using a T4 GPU runtime because we need GPU, even a basic GPU for this exercise. Now we are starting with importing and installing all the dependencies which are required for us. We are installing transformers and torch libraries, and then we are importing from transformer auto model for causal LM and auto tokenizer. This helps us in loading the pre-trained model weights and the available tokenizer for the relevant model. Now let's see what is our baseline model. So for this exercise, we are using GPT-2 large as a baseline model. This model has around 775 million parameters, and we are also importing the relevant tokenizer, and we are setting it to the eval mode because we are not doing any kind of training here. As you can see in the logs that it is importing the tokenizer config, the model config, and the vocab and everything. And the model size itself is 3.25 GB, which is roughly 4 times the number of parameters, because we are loading this model in a FP32 data type. Now we will compare decoding with and without KV caching. So this is our benchmark function where we start a timer, then we do model.generate call with the given input. We also provide the maximum number of new tokens which we want to use, and then this is the important parameter, use cache, which tells the model whether we want to cache the key value pairs for the previous tokens or we do not want to keep them. So this will be the differentiating factor. Now let's run this cell. So we are computing latency with caching, and we are also computing latency without caching for this GPT-2 large model. And as you can see, if when we use the KV caching, it takes 3.4 seconds to generate the response, but when we do not use KV caching, it takes 4.49 seconds to generate the response. So here you can see clearly that we have around 31% gain in latency just by setting a single parameter. Of course, there is much more happening behind the scene, like how the GPU is facing a memory spike up and all those things, which you can clearly see using the NVIDIA SMI command in your GPU. But here you can clearly see that we are getting a 31% improvement in latency. Now let's also look at FlashAttention in action. Now for this FlashAttention demo, I'm using a TinyLlama 1.1b model because this model naturally supports FlashAttention. It is inbuilt. For other models, we need to have specialized kernel to support FlashAttention. Now we are loading this model and then we are setting it to eval mode as we did for the earlier model also. Now after loading this model, we are running the latency benchmark for this model as well. So I run it with this prompt: artificial intelligence is transforming the future of. And for this given prompt, I am computing the latency with the baseline model, and I'm also computing the latency with this FlashAttention enabled model. And after running this cell, I can see the baseline model is doing this computation or this response generation in 2.6 seconds, while the TinyLlama, which is the FlashAttention model, that is doing it in 2.37 seconds. So here we have a clear speed up of 10%. Now you should notice one thing, that even though our baseline model was small and our FlashAttention model was roughly 30% bigger than the baseline model, still we are seeing 10% relative speed up. So you can imagine if your models are of same size, you can expect 25 to 35% relative speed up just by enabling FlashAttention. So we saw how to enable KV cache in LLM decoding and how it helped with the reduction in latency. We also saw the FlashAttention in action, which further reduces the latency. Next, we will dive deep into PFT techniques to avoid catastrophic forgetting and efficient fine-tuning LLMs. Imagine you have got a pre-trained 7B parameter model, Llama, Mistral or GPT. It's fluent, smart and packed with knowledge up to 2024. But now you want it to do something very specific. Maybe understand medical notes, maybe speak like a financial analyst, or maybe answer customer support tickets for your startup's product. Here's the problem. Full fine-tuning takes days of GPU time, terabytes of storage, and infrastructures most teams don't have. So what do? That's where PFT or parameter efficient fine-tuning comes in. Think of it like giving your model sticky notes, quick reminders to adapt its behavior without rewriting the entire textbook. Instead of updating all the weights, PFT freezes the big base model and just inserts tiny trainable adapters. These little modules learn the domain-specific knowledge while the heavy lifting stays frozen. The result? Way fewer parameters to train, lower GPU memory requirements, faster experiments, and no massive checkpoints. One of the most popular methods here is LoRa, low rank adaptation. Most of the heavy cost in transformer comes from those giant linear layers. LoRa says don't touch the giant matrix. Instead, we just add two small matrices, one that compresses the input down and another that expands it back up. Those two tiny matrices are the only parts we train. It looks like this, where W is frozen and A and B are two tiny trainable pieces. These A and B are basically your low rank matrix factorization of delta W. So, when do you use PFT or LoRa? When you want to customize a base LLM for a specific domain, when you are limited by hardware or compute budget, when you need multiple variants of a model, say summarization, Q&A, and code generation, all from the same base model, and when you want modularity. So one base model, plug and play adapters. That's why PFT is everywhere, from healthcare NLP to finance chatbots to legal document summarizers, and especially in startups that can't afford full retraining. In fact, many of the fine-tuned LLM or Mistral models you see on Hugging Face, they were built with LoRa under the hood. Let's visit LoRa, one of the most prominent PFT technique in our next hands-on demo. In this lab, we will fine-tune GPT2 using LoRa on a financial Q&A dataset. We will measure training time, memory, and resulting performance versus full fine-tuning. Let's dive deep into the code. Now here, we are using a Jupyter notebook with a T4 GPU, which is easily available on a Google Colab notebook. Now, we will start with installing all the dependencies and importing them as required for this exercise. So since we are doing a parameter efficient fine tuning, we are installing PFT library, and then we are also importing from transformer auto tokenizer and auto model for causal LM, which is very useful to train, which is useful to load any pre-trained model and any pre-trained tokenizer. And then we are also importing get linear schedule with warm-up, which is useful for scheduling the optimizer for our training. And then we are checking if we have a GPU device available or not with this command. So since we are using T4, we have it available. As you can see, the cell output is device equal to CUDA. Now this is our toy by financial Q&A data set. You can create it easily using any of the open source LLM. And now out of these 32 questions, we are keeping 16 for the training, and the other 6 and the rest of the 4 samples we are using for validation. So in total we have 20 samples here. And now we are converting this to a dataset dict where we have the training and validation keys available. Now comes the tokenization and labeling part. Now we are using GPT-2 large as our base model. This is the model we will be doing full fine tuning and LoRa fine tuning with. So we load this model and we set the maximum length equal to 256 so that we do not overflow the T4 memory. 256 can easily fit into this. Now we have a function to build an example. Here we are doing nothing, just we have the questions and answers. So we are getting the question IDs and answer IDs. So, and we set the label as -100 for all the tokens corresponding to the question, because we do not want to do any loss back propagation on those tokens. And we set it to the non-negative 100 for the answer token IDs, because we want to do back propagation for the answer tokens. Similarly, we define a function for call it. The basic thing this call it function does is it equalizes the sequence length for all the examples in a single batch. That is true for your input IDs, for attention mask and labels. This is useful to fully and efficiently use your GPU kernels. Now coming back to the validation metrics, here we are defining the perplexity metric, and the perplexity metric is basically exponential of your log probabilities for the entire sequence. So that's what we have defined here. And we have a function to calculate latency also, the generation latency. As you can see, we first tokenize any prompt, then we start a timer, then we are generating with few of the arguments. We are passing the maximum number of new tokens, and we are also passing the tokenizer which we want to use. Now let's come to the 2 fine tunings which we want to do, and then we will compare the results. So first we start with the full fine tuning. Here we are setting that okay, gradient checkpoint is enabled. We are using accumulation steps equal to 2, so that we are not updating gradients every step but every 2 steps. And then we are also setting the maximum number of training steps as 40. And then we have number of epochs equal to 1. So once we have passed through the entire training data, we will not do the second iteration. We are setting optimizer as Adam optimizer, and if you look at carefully, we are using it on all the parameters of our beast model, and you will see how different it is in the case of LoRa. Now for the number of epochs, we are passing each batch through the model in this line, and then whatever loss we are calculating, we are doing loss dot backward, so that we have the gradient for all the weights. Now if the current index is equal to, or is it divided by the accumulation steps, it means we need to update the all the weight parameter. So that is what we are checking here. Once we are done with this step, now we are calculating the perplexity of this fine-tuned model, and we are also checking the generation latency. So as you can see, we ran it for 8 steps. The maximum memory which hit during the training in our GPU is around 7.5 GB. The generation latency is 1.664 second for the given prompt. Our prompt was what is EPS, and the perplexity is coming out as NAN because this model is not trained properly. So it is likely that we are getting close to 1 probabilities for some random token in the output, which is making the perplexity NAN, because we are having a 1 divided by 0 term here. Now let's come to the LoRa fine-tuning part. Here we are using a 8-bit LoRa, which means we convert our beast model to 8-bit quantization, and then we have the LoRa weights also into the 8-bit. Once we complete the training, we transform all of them to the 16-bit. This is to save even more at the time of training, but there is additional overhead because we need to convert all the weights of the beast model to 8-bit, and we need to dequantize to 16-bit. Here again we load the beast model, and then we have this LoRa config where we set our LoRa alpha and LoRa dropout. So this R is the low rank matrix factorization number. So you are decomposing using 8-dimensional columns your update weights. And now we see you are training it for same number of epochs. You have set maximum number of steps. You have set the learning rate also. You are using the same kind of optimizer as well here. As you can see, we are using Adam W optimizer. Now we will run it for the number of epochs, and if we are hitting the maximum number of steps, then we will break and we will stop the training. Again, we do the perplexity evaluation and we calculate the latency of LoRa model for the same prompt because we want to have a fair comparison. When we run it, we see that perplexity is 15.99 and the generation latency is coming out to be 5.34 seconds. But these are not the important metric which we want to pay attention to. The important metric is maximum memory. As you can see, when we were doing full fine tuning, maximum memory was 7437 MB, which is now reduced to 2631 MB. So the bottom line is, even when you are resource constrained, you do not have enough GPUs, you can use LoRa kind of PFT to fine tune any big LLM within your system with limited compute budget. So that is the exercise which we covered in this one. Now if we look at the summary, we are also showing that okay, if you do the full fine tuning versus you do the LoRa, what is the comparison in the accuracy, what is the comparison in the generation latency, and the maximum GPU memory which we are hitting. Be mindful that since we were doing it on 8-bit base, there is a extra overhead of quantizing and dequantizing the base model weights. So that's why we are seeing average higher step time for the LoRa part. Okay, now let's do the sanity evaluation using both the models. So our test prompt is, let's say, what is EBITDA, what is P by E ratio, what does ROE measure. And if you look at the output, when I'm doing the generation using the fine-tuned model, I'm getting very gibberish output. There is only one single exclamation mark and it is repeated. But if I look at the LoRa output, you are seeing the proper definition of EBITDA, you are seeing the definition of PE ratio and everything you needed for this financial knowledge. So you see the LoRa in action and how it works. We see our LoRa slashes training time and memory requirement drastically while retaining most of the knowledge of the base model. It is a very promising candidate for personal AI use case where the base model is the same for everyone, but on your own smartphone, the model is fine-tuned with your own personal data, and that too only on your phone. Alright, let's take a step back and look at the ground we have covered in this masterclass. We started with the pain points, brilliant models that break the moment you try to deploy them. Latency spikes, memory overload, ballooning cloud costs. And then, step by step, we built a toolkit to fix it. We learned how to make models smaller with distillation. We made them lighter and faster with quantization. We tackled token latency using speculative decoding. We stretched context windows with efficient attention. We served models smarter with KV caching and kernel fusion. And finally, we made them adaptable with TFT and LoRa, tuning for new domains without retraining from scratch. Each of these techniques answers to some core questions. How do we make LLMs cheaper, faster, and more accessible without losing their magic? Now, here is the thing. Optimization isn't a one and done step. It's an ongoing process. As models evolve, as hardware shifts, as new use cases appear, you will need to keep exploring and adapting. So my encouragement to you, don't stop here. Try quantizing a model you use daily and measure the difference. Plug LoRa adapters into a base model and see how quickly you can create a domain expert. Experiment with streaming responses and watch how perceived latency changes for users. And share your journey, post your benchmarks, your tricks, even your failures, because that's how the whole community learns and pushes forward. So, congratulations, you have just leveled up from running models in a notebook to optimizing LLMs for the real world. And the next time someone on your team asks, why does this chatbot feel so slow? You will have an answer and a fix. Thanks for joining me in this NIIT Masterclass. I can't wait to see what you build faster, leaner, and smarter than ever before. And as always, let's keep building.